Let's begin. Good morning, good afternoon, good evening, everyone. Welcome to today's or the webinar. Today is our great pleasure to have Michele Rinaldi speaking with us. Dr. Rinaldi got his PhD from University of St. Andrews, UK, where he's currently holding a postdoctoral position at Trinity College, Dublin. And his PhD work, I believe, that has been working on the equation state of water and extreme conditions. I believe that was the continuous work from the Deep Carbon Observatory program, and he extended that system beyond Earth system to the Mars. So today he's going to talk us more about the new cutting edge breakthrough from his research. So normally our webinar goes for about 40 to 45 minutes, and this is an online webinar. It's relatively flexible. And then we have another, like say, 10, 20 minutes of interaction with our participants today. And all the contents will be recorded and posted on YouTube to advocate science, as well as equation of state of water and extreme conditions. And with that, Dr. Rinaldi.
Thank you very much for the nice introduction. So hello, everyone. Thank you very much for having me here. It's always a pleasure for me to give a seminar and being invited for a seminar and discuss a little bit about science, what I do. So today I'll be talking about metasomatism on Mars. And by the end of this talk, I hope to somehow convince you that also deep processes like fluid rock interaction in the crust or in the mantle could be actually a potential source for methane in the Mars atmosphere. Now, at the beginning, I want to give you a sort of broad introduction about Mars and what we call the red planet. Now, 3 to 4 billion years ago, Mars was very, very similar to Earth. So we can say that Mars was sort of the little brothers of Earth because it was basically the same. He had a magnetic field, not as strong as Earth one, but he had a magnetic field, he had an atmosphere, and especially had liquid water on the surface. But as you can see here from this picture, from Perseverance, one of the rover we had on Mars, well, today is completely different. So it looks like more a desert than actually a habitable planet. But why it happened? Well, there are many reasons why Mars nowadays is different than what it was. So first of all, we know that Mars is actually smaller than Earth, as you can see here, 3,390 kilometers in radius. Earth is about 6,400, so it's almost the half. So the volume of Mars is definitely lower, but especially, as you can see here, the lower density. Mars has about 3.9 grams per cubic centimeter. Earth is about 5.5, so there is a huge difference in density, and this difference is somehow related to some compositional differences between the two planets. I'm not going too much into detail about the different compositional aspect of Mars. I just talk briefly later about iron, because it's the only one we actually need for this talk. But they are sort of both terrestrial planets, but they have interesting differences. It's geologically inactive, so we know there was tectonic evolution on Mars billion of years ago. Right now, Mars is basically dead, so there is no convection anymore. The few heat actually produced inside Mars is related to radioactive elements, but it's basically a dying planet under a sort of geological point of view. There are a few speculation that it might be a little bit factive, but well, I'm not gonna say that's right or not. It really depends on the speculation, the assumption you actually use. There is no magnetic field, so this means that there is a very thin atmosphere, and as you may be aware, so far we hadn't found any sort of form of life here, so apparently this thin atmosphere is not enough for having any life there, and especially such a thin atmosphere actually does not allow liquid water on the surface. So the surface temperature is minus 65 degrees, all the water is in the poles and in under the form of ice, so it's there is no water actually. The internal structure of Mars is a little bit more interesting for, at least for a geologist like me, especially because Mars and the Earth are basically has the same structure. As you can see here from this picture, we have a crust, it's a silicate crust. There isn't much of compositional difference between Earth crust and Martian crust except for the iron, and it's 40 to 60 kilometers thick. It depends which part of Mars you're considering, and a few other assumptions, but overall the MO is between 40 and 60 kilometers, and the pressure at this layer, I mean, at the MO is basically 0.5 gigapascal, 0.6 gigapascal, and this will be very useful for the models I'll show you later. You know, if we look at everything else, for example, the upper mantle, olivine plus pyroxene plus garnet, it's basically the same rocks at Earth. I mean, there is almost no difference. The chemical composition of those rocks are actually, well, different, more iron richer, basically. But the classification of the rock work anyway. So we have peridotites, websterites, pyroxenites, gabbros, and so on. So there aren't many differences under, let's say, the mineralogical point of view between Earth and Mars. And we can go lower. We have the lower mantle with high pressure minerals. And then we have this core, which is iron, nickel, sulfur. Apparently there is more sulfur than the one we got on Earth, and therefore it could explain some differences in the density between the two planets. But for the purpose of this talk, actually, one of the most important thing is that we got meteorites on Earth, basically. So I will say by luck, basically over the geological time, some rocks from Mars actually fall on Earth. And so we can actually get our hands on them. They're very rare. As far as I know, there are less than 200. And so we managed sort of to understand how Mars is. And so we ran some geothermal barometry. We ran also some oxygen barometry. And oxygen barometry says that at basically any level from the surface to deep in the mantle in Mars, well, that planet is much more reduced than Earth. So it's between 0 and -3 FMQ at the cross-mantle boundary. So this means that at 40 to 60 kilometers deep down in basically in the Martian mantle, at this boundary, we have a very reduced condition that, you might already know where I'm going. Basically, I'm talking about methane, so it's a reduced species. So, you know, having a very reduced condition is something that we really want to. What about the temperature inside Mars? Well, as I already said, Mars is sort of dying. The geothermals are getting more steeper day by day, basically. And you can see here, 4 billion years ago was sort of similar to Earth. Right now is very, very cold. I mean, we're talking about probably 100, 200 degrees at almost 65 kilometers. So it's a very cold planet. And but why we are so interested in Mars, actually, and to understand this, we have to talk a little bit about the Martian atmosphere. So Mars has no magnetic field, so the atmosphere is very thin, constantly stripped by solar winds and radiation. And this means that, well, there is not enough heat on the surface to stabilize liquid water. And we have a lot of carbon dioxide. So we could say that Martian atmosphere is actually a mixture between carbon and oxygen. But the thing is, inside Martian atmosphere, we have this methane. It's a very, very, probably less than 1% in volume. It's very, very small amount, but it's very important. And especially in the early 2000, about 2002, I believe, we realized there are sort of variation, seasonal variation in the amount of methane in the Martian atmosphere. And this is actually, well, very interesting. But to understand why these seasonal variations are so interesting, we have to understand where the methane comes from. So I switched for a little on Earth. So, well, I'm not going to talk about Earth atmosphere. We all know that it's basically made by oxygen and nitrogen, but still, also on Earth, we have methane. So if we check where this methane comes from on Earth, at least according to the USA Environmental Protection Agency, for this one, it should be 2023. So last year, as you can see here, we got methane produced by landfills, manure management, coal mining, and many other also natural gas and petrol system. It means that during the extraction, we lose part of the methane and so on. But all of this, so from the landfills here, clockwise, to the natural gas and petroleum system, 75% of the methane produced by, well, released into the atmosphere is related to, well, some sort of industries or companies. So it's something human-made, let's say. But the other 25% is the entering fermentation, which means basically that is related to life. In other words, in simpler words, I mean, I'm not a biologist, I won't go into too much into details about this, but at some point during the life cycle, almost every life organism, we can actually produce methane. So 25% of methane currently in the atmosphere is produced by living organisms. And this is extremely important because, you know, let's assume like Mars, a place like Mars where, well, luckily and obviously there are no people there, at least right now, there are no industries. So we can rule out all these 75%. So at the beginning, we really thought that the methane we found on Mars actually was sort of related on life. To date, we couldn't find any form of life of Mars, so we know that methane somehow a biosignature, so sort of tracer of life on other planets. But we are all geologists, so we know also that, you know, geological processes such as eruptions or volcanism or secondary volcanism and so on can actually release a high quantity of methane in the atmosphere. It might not be relevant in the short term, but over geological timescale, this is extremely relevant. And sometimes in the literature, we actually forget that, yeah, methane is definitely a biosignature, but it's still something related to our planet, to geological processes. So I'm not talking about life in space. I would love to, but I'm a geologist, so we'll talk about geological methane. So part of this methane that comes from geological environments, especially on early Mars. Why on early Mars? Because I believe it's much more interesting than the, let's say, nowadays Mars, because 3 to 4 billion years ago, probably also 2 to 4, Mars had a magnetic field and an atmosphere, and especially there was liquid water on the surface. And you probably already know this. It was one of the, let's say, biggest discovery of the last 40 years. You know, a very dry planet nowadays had a very big water flows on the surface. How do we know it? Because this is just an example. So you can see here, this was basically a river going into, I don't know, was a sea or lake or something, but this one is basically a delta. And the morphological and sedimentary structure we actually find in this area, confirmed by then all the rovers that actually pass by, they're basically exactly the same of what we see on Earth when we have flowing water. So we know that at some point during Mars life, basically, there was basically some liquid water, but how it's possible? The magnetic field on Mars wasn't strong enough to stabilize actually a thick atmosphere like Earth one. So how can we increase the temperature above 0 degrees to get liquid water? Well, using methane. So there are many models in literature. I'm not going to discuss all of them because they are fairly complex, and the most important things that you know for this talk is that methane is actually a stronger greenhouse gas than CO2 and CO. So this means that if you replace CO or CO2 in an atmosphere, we increase the surface temperature because methane is very strong greenhouse gas. So it is believed that Mars had a CH4-based greenhouse, which means at least about 10% of methane in the atmosphere that could increase the temperature above 0 degrees, and therefore we have liquid water. How do we get the methane into the atmosphere? Well, all the different geological processes. Most of them are sort of well known. All the volcanic parts are very well studied in literature for both Earth, and there are many models for Mars. So I wanted to do something sort of innovative. So my idea was to do something much more deeper than the traditional model. So this is just a nice, let's say, scheme representation of the idea I had in mind when I devised this project. So there is a cross-mantle boundary on Mars, 0.5 gigapascal, about 40 to 60 kilometers, as we already discussed. The temperature goes between 300 and 800 Celsius degrees. It really depends on the geotherm you want to use, but it's sort of a bit of a nice range for what is happening basically inside Earth under temperature point of view. So we can assume there is a magma chamber. There was a magma chamber when Mars was still active, and this magma chamber emplaced in between the crust and the mantle. So we all know that during magmatic processes, well, there are volatiles in the magmas, and lowering the temperature, we slowly release all these volatiles, making a fluid phase, and the fluid phase can interact with the wall of so different rocks basically, and they can also, I can see here this arrow, the fluids are very well known to be very mobile, and therefore they can actually travel hundreds of kilometers, at least on Earth and probably also on Mars. Therefore, there is sort of fluid rock metasomatism going around. We have evidence actually that actually Mars has carbon and fluids inside the mantle. I will slightly talk about this later, but the thing is, we found fluid inclusion, or what we call the macromolecular carbon. So basically, carbon-rich fluid inclusion in ultramafic and mafic minerals. So we know that in the Martian mantle, there are fluids. And so the idea is, what if in a such reduced planet like Mars, where there is a lot of iron, there is a lot of, well, the oxygen fugacity is very low, what if fluid rock metasomatism happens, and, well, what's the most stable carbon species inside such fluids? So the question is, can we model it? Because it's all comes to this. I mean, I always work with thermodynamic modeling, so I really want to model this process that could happen on Mars. And the answer is yes, obviously, otherwise I wouldn't be here today. And we use the deeper water model, it's the DEW. The deeper water model is currently the only thermodynamic software can actually model properly the fluid rock metasomatism. But because if we take other softwares like Thermocalc, Faxage, Perplex, the fluids are actually made by components. So there's just water, CO2, maybe CH4. That's it. The truth is, fluids are much more complex. There are at least, well, there are not at least, there are many chemical species, and these chemical species are what actually control the fluid rock metasomatism. Now, the deeper water model involves more than 50 chemical species, so it's the perfect tool for studying fluid rock metasomatism. So it's in the future, you'll need to model something about some sort of metasomatic process. The deeper water model is the right software for you. It works up to 6 gigapascal at 100 Celsius degrees, and it's more than enough for most of the applications. How it works? Well, first of all, we need to model a fluid. And how do we model a fluid? We take a rock. So for example, let's assume we take a Martian lerzolite, okay? A Martian peridotite. We put some water in equilibrium with that peridotite. We wait for a long time, we reach the thermodynamic equilibrium, then we get that fluid. And so we get a peridotitic fluid because it was in equilibrium with a peridotite. Then we move away this fluid, we make interact with a different rock, and the different rock is not in equilibrium with the fluid anymore, and therefore there is a chemical gradient triggering irreversible mass transfer reaction. In other words, there is a metasomatism. This metasomatism means new metasomatic minerals and new metasomatic fluids. For this talk, I'll be talking about specifically fluids, the amount of methane inside these fluids, but I've also studied different sort of minerals resulting from this metasomatic interaction on Mars. So if you're interested, everything is in the paper is published. Today, for the sake of time, and just talk about the fluids. This is a very broad explanation of how the deeper water model works. If you are interested in all the technical details, equations, so on, Wangas-Verjensky 2020 is the right paper for you. It has all the details, and it's you should check it out in case, or you can text me, or you can text Dimitrius Verjensky, which is one of the person who actually developed this method. So we need to at least find a fluid for our fluid rock metasomatism model, and we need to find the rocks for the modeling process. So let's start with the rocks. We don't know much about what's inside Mars. Oh, but we basically know almost nothing, actually. All the information we have are from meteorites and some information about the rover we have on the Martian surface. The thing is, on the surface, everything is basically altered, so there is nothing fresh, and it's very hard to understand if, well, what was going on basically on Mars. So we have to rely on meteorites, which are our best choice. There is a whole classification about Martian meteorites, so I'm not going into it because it's not necessary, but as you can see here, someone ran oxygen geothermobarometry and geobarometry on these meteorites, and we can actually split the meteorite in two parts. Let's say the Shergotite source is sort of shallow one, up to about 2 gigapascal, so 120, well, almost 200 kilometers down to Mars, so it's fairly deep up, actually. So it's the part I would love to focus for all the models. And then we have all these deeper sources, it's harder to model, and actually for the purpose of, trying to explain why metasomatism could be a way to release methane into the surface, I just want to study, let's say, somehow shallow processes. So we just focus on this part. And when we look at the rocks inside, they're always the rocks we know. So we got two, basically peridotite, alerzolite, and dunite, two pyroxenites, orthoperoxenite, caloperoxenite, and a mafic rock, a gabbro. So what I did basically was to go through the literature, collect data, and so get the mineralogical composition of 5 of these rocks. As you can see here, what I basically reconstructed the mineralogy and the solid solution through basically some calculation. The thing I want to stress about, for example, let's check this lertzolite, as you can see here, forsterite 0.65. So we all know that if we take a lertzolite in the Earth mantle, olivine is usually 92, 93 forsterite. It's one of the few things all the mantle geologists actually agree. So we know that Earth mantle is very magnesium rich. What about Mars? Well, Mars is extremely iron rich, and therefore we can, well, in a lertzolite, we have forsterite 65. We can go, for example, on a clinoperoxenite, forsterite 45. So the rocks themselves are sort of the same, but actually their composition is completely different. That was the easy part, but what about the fluids? I mean, we barely know what kind of fluids we got on Earth, and we almost have no information about the fluids we got on Mars, basically. We know there are fluids because I've already talked about the macromolecular carbon found as inclusion in mafic and ultramafic minerals. We found also apatites in association with mafic and ultramafic minerals. So there's definitely some sort of water circulating in the crust in the mantle. And we very, very barely constrained at least 2 different reservoirs on Mars. As you can see here, Martian mantle. So isotopically speaking, low deuterium, and the Martian crust is actually richer in deuterium. So it's we don't have really enough data to constrain the two different reservoirs, but at least we know there are there actually. So we all know there are fluids inside Mars, but we don't have any composition. So how could they choose a metasomatic fluid for the deeper water model? Well, I used a comparison with Earth. So we know there are fluids inside Earth's mantle because we have diamonds, basically. Diamonds has actually fluid inclusions. And from this fluid inclusion, we know there are at least four compositions. Now, the first one is silicic composition. Another way to call it is eclogatic composition. So eclogates mean basically a sort of tectonic environments. I don't know if there were actually such environments on Mars, and we couldn't find any eclogates, meteorites. So I just didn't want to use an eclogatic fluid just for the sake of the modeling. So I want to choose something else. Saline composition and carbonated composition, you might know them. They are very crazy fluid. It's very hard to understand where they come from on Earth, and especially the saline composition is really crazy. It has so much sodium and potassium that it's basically impossible to model. So they're very harsh fluids. So it was too risky to model them. And therefore, I just stick with, well, a peridotic composition. We know there are peridotites in the Earth, the Mars, inside Mars, in the Martian mantle. We use them for, as I showed you before, we use lertzolite and dunite. So for sure, there must be some peridotic fluid around the Martian mantle and crust. So what I did was to put some water in equilibrium with, let's say, Martian meteorite. Obviously, on a modeling point of view, I didn't do it practically, just all on modeling. And so I got a peridotic composition for our starting fluid. So as a summary of my modeling approach, we have 5 different rocks: lertzolite, dunite, orthoperoxenite, and clinperoxenite. So 4 ultramafic rocks and 1 mafic rocks, gabbro. 1 metasomatic fluid with, let's say, an easy peridotic composition. The conditions are crust mantle boundary 0.5 gigapascal and between 300 and 800 Celsius degree. And I'm trying to simulate the cooling of a magmatic chamber. It goes from 800 to 300 Celsius degree and keep releasing fluids at the same temperature and pressures. Oxygen fugacity between 0 and -3, so a perfect environment for methane. And I also changed the fluid rock ratio because, you know, when you talk about metasomatism, fluid rock ratio is essential. I use moles to moles. I know it's not something common. You rarely see moles to moles, but for chemical modeling, it's basically the best way because for writing reaction and so on. So I kept using moles and over moles. So the results. Before diving into the results, I want to show you this. I mean, I'm considering 0 FMQ, which is actually the worst condition for on Mars for forming methane. Why I choose to plot everything at 0 FMQ? Because I want to show you that also in sort of not the best conditions, you can actually form a lot of methane. So, you know, we see it a little bit later, but once you lower, you have lower oxygen fugacity, the amount of methane can just improve. Therefore, I want to put myself in the worst conditions and then show you what happens. So on the left, we have peridotic fluid interacting with a lertzolite. And if you check, basically, if you see here, 800 degrees, we have only 2 species. It's 2CO3 and CO2. So very common species. There have been recently published a paper that actually proved that these 2 species are actually the most common ones in fluids, at least on Earth. But I suppose thermodynamic works also on Mars, so there is no point to doubt that also these 2 species are actually very common at high temperature. But as soon as we lower the temperature until, let's say, 470, 480, as you can see here, the red line is methane. So at this point, methane becomes dominant and everything else is actually losing, basically. So down to 300 degrees, we get basically almost 100% methane. Don't mind about this field, the methane metastability will be useful later, but so far, if you look at this red line, methane drastically increases with the temperature, which is very, sorry, increases with decreasing the temperature, which is very cool because it means that lowering the temperature of a magmatic chamber triggers methanogenesis. So we will have more methane. As you can see here, on the right, different rocks, 4 rocks, the dunite, clinoperoxenite, lertzolite, and orthoperoxenite keep increasing their amount of methane, lowering the temperature, which is great, but the blue one is the gabbro. So the only mafic rocks we have are, well, it's not the best for the methanogenesis. It's not that bad still. About 15% of methane, but not that good as ultramafic rocks. So the first take-home message is that methanogenesis increases at low temperatures, and we really like it. And ultramafic system produce a higher amount of methane than mafic system. So if you think about early Mars, but also early Earth, actually, ultramafic systems were much more common, for example, comatiites. So I'm happy that ultramafic system can produce more methane than actually mafic ones, because it means that potentially 2 to 3 billion years ago, we actually, well, we had much more methane than in the later stage of the Martian history. So this is a very good and interesting point. Result number 2 is the fluid rock ratio. And so this one on the left is the different carbon species. I want to show you also dolomite. And it's very nice here because we actually found carbonates on Mars. So dolomite is actually something it's possible to form. And I'm happy that my models actually sort of, match with the nature, because they should always match with the natural data. But as you can see here, gabbro, so not the best lithology for methanogenesis, but still, as soon as we increase the fluid rock ratio, the red line increases. So a very high fluid rock ratio, methane becomes dominant. And it's same basically for all the other lithologies. As you can see here, below 2, let's say, fluid rock ratio, the amount of methane is not actually, well, it's still good, but not that good. Above 2, basically methane becomes dominant. So increasing the fluid rock ratio is always a good thing, obviously, except for dunite. We sort of lose it from 100% to 80, but it's still a lot. So I'm more than happy to lose a little bit of methane if all the other rocks actually increases the methanogenesis. So the second take-home message is that different lithologies behave differently when changing the fluid rock ratio. This is very important because if you already look in the literature or other models, actually, well, very often they actually don't consider different lithologies, and when they consider, they sort of behave the same. But actually, in all my models, all the 5 different lithologies have not very different, but different enough behavior. And this is also one of the strengths of the deeper water model, and that's why it's actually very good at reproducing natural data. So different lithologies behave differently when changing the fluid rock ratio, and higher fluid rock ratio is actually much better for methanogenesis. And this is also coherent because, at the end of the cooling process of magmatic magma chamber, for example, the solubility between fluid and mets actually drops because lowering the temperature, the solubility drops, and therefore we release much more fluid. And so this is another proof that lowering the temperature is very good for the methanogenesis. So it's coherent also with what I show you in the results 1 and what other, let's say, evidence in the literature. Results 3 are a little bit, to me, not that relevant, but they're still good to talk a little bit about this. As you can see here, different carbon content. So molality means number of moles over a kilogram of solvent, so a kilogram of water. It doesn't really matter. I studied different from 0.1 to 2 molal, which is according to the data we know about fluids on Mars. It's actually a reasonable value. And you can see here the amount of methane, it doesn't really change. So my models predict that the carbon molality, sorry, doesn't actually change anything inside the system. But the oxygen fugacity actually does. That's why, as you can see here, I put myself in the worst condition when methane is not that really common. Sorry, I mean, it's very obviously dominant, but not as dominant as other FMQ. From -1 to here, was supposed to be -3, was a small mistake. But as you can see here, methane becomes dominant. So as soon as we reach -1 FMQ, all the carbon in a fluid directly goes into methane. So the carbon content has a very minor influence over the carbon speciation. And at FMQ minors of -1, methane is just dominant. On a place like Mars, on a planet like Mars, methane is basically, well, the dominant carbon species in a fluid. There is obviously a problem about what I'm talking. I mean, what I show you so far is that we are talking sort of very deep processes. When we are talking at least 40 kilometers down from the surface of Mars. So, 40 kilometers are a lot to go through. So one of the questions I've got also during the review, but every time I actually do this talk, say, how is possible that, okay, let's say you demonstrate that there is a lot of methane inside the crust and the mantle on Mars, but how is possible that this methane actually gets to the surface and contributes to the atmosphere? Because what's the whole point of this paper? Well, it could be much easier than we thought, because we know for at least 30, 35 years that methane below 400 degrees, actually methane is metastable inside a fluid. So it means that the only way below 400 or 300 degrees, it really depends on a few assumptions, but below 400 degrees, methane does not react, or better, it's a metastable, so it's not stable anymore. Methane wants to react, wants to participate to chemical reaction with rocks or other chemical species. The problem is the kinetic of such reaction is so slow that it's not feasible, not even in geological times, basically. So this means that, we can trap, store, and preserve methane over geological times on Mars, simply because methane does not react. The only way you have to basically make this methane react is burning it, as we all probably know, some cars works in that way, or the kitchens and so on. But as far as you're in a fluid, you don't have really this problem, and therefore you can just preserve the methane. Besides, if you remember at the beginning, I showed you that Mars is a very cold place. Mars has a very cold crust. Right now, some estimations say there are about 200 degrees, 100 degrees at the mole. This means, as you all know, a cold rock breaks very easily. So the Martian crust is very fractured, and fractures are actually canals for basically releasing gases from deep down to the crust. So I'm not saying this is common. I have no, how can I say, have no evidence that this process is common, but it's actually much, much easier than we actually thought before this work. So methane can be actually preserved and transported up to the surface and could contribute to the formation of CH4-based greenhouse. A little bit more work is needed. I'm working right now on trying to modeling all the raising process of these fluids. It's much more complicated because the crust is always more, let's say, petrological and geochemical, more complex than mantle, but sooner or later I'll get there, and hopefully soon. Well, on my final slide, so I'm almost done. I was just to give you an idea how much methane can we actually produce in fluid rock metasomatism. Well, much more than what you will think. So I basically devised this very simple equation. There are many terms, but they are all very simple. So two components. Rock component is volume, density, and molar mass of the reactant rock. And everything that you can easily calculate or recalculate from data. So it's all, we have all of these parameters. For the fluid component, it's a little bit more tricky, but we have fluid rock ratio, the carbon molality, the molar mass of water, but obviously known. The fluid, sorry, this one was the fluid rock ratio. This one is the fraction of methane in the fluid. So you need a little bit more assumption, but you can actually get there if you run a few models. Still FMQ equal to 0 for this calculation. So worst case scenario for me. And we can get almost 10 kilograms of methane for cubic meter of reactant rock, which is a lot. If you think about that, for each cubic meter of a reactant rock, we can get 10 kilograms of methane. Well, maybe we won't preserve all of it up to the surface, but still we will actually, well, it's enough for sort of sustaining the CH4-based greenhouse. Now, as you can see here, the first four rocks are ultramafic rocks, goes from 3.5 kilograms to 10, so a very high amount of methane. Gabbro, the only mafic rock, is slightly lower. Well, I already show you all the plots. It's mostly related to calcium. Gabbro is much richer in calcium, therefore there are a few problems with the carbon speciation with calcium. But still, half a kilogram of methane in a metasomatic fluid interacting with a cubic meter of reactant rock is not that bad, not that bad at all. So potentially, the process I actually show you is a very good source for methanogenesis for methane, actually. So these are the conclusion. I'm not going through all of them because it's basically what I've been discussing for the last 40 minutes. The only take-home message is that we know there are fluids in the Martian crust and mantle, so we know that there is a metasomatic environment. We cannot constrain it properly right now. It's we need much more investigation and hopefully much more data than the one we got from the rovers and from the meteorites, but still we know this is possible. Now, thermodynamics works also on different planets, so it should be something we can easily model with some assumption. It's true, but all the data I show you, they shouldn't be taken as quantitative models because there is no quantitative models for Mars, but should be a qualitative model. So this means that a metasomatic process can actually produce enough methane, and that methane can be stored, preserved over a geological timescale, and somehow it can easily reach the surface and contribute to the CH4 greenhouse. I don't know how much in percentage this process actually contribute to the CH4 greenhouse, but so we need further investigation for this. But it's a possibility that I wouldn't rule out, actually. So this is the end of my talk. There are many more details in this paper. This is all the reference, so you're more than welcome to text me or ask me a question, and or if you prefer, the paper is available on EPSL, and yeah, that's it. Thank you very much.
Okay, thank you very much, Michele. And now it's time for questions from our participants. So if you have questions, feel free to open your mic to ask a question. Alternatively, you could leave the question in the chat and I could read the question on your behalf. So any questions from our participants today?
Hello.
Hello.
Hi, my name is Hui Zhuangli. Thank you for the excellent talk. I really enjoyed it. So I'll start with a general question, and I don't know if I missed it, and I'm just thinking if it's more reduced in the Mars interior, maybe the gas released from the magma could contain quite a bit of methane. And I'm just wondering that the amount of methane released through magma, is it more than the metasomatism produced methane, or I'm just I always have this idea that magmatism will be more like a bigger scale process than metasomatism. That's my basic thinking.
Well, yes. Generally speaking, I believe you are right. The thing is, most of the time we think that fluids cannot exist as isolated fluid phases into a magma chamber, but actually they could exist. So I wouldn't rule out the metasomatism at all. I know that obviously magmatism in a magma chamber is much more important, and the fluids definitely will interact with magmas and so on. And it's what basically contributes to primary volcanic carbon, so all the eruptions, secondary magmatic carbon, so like geysers and so on. So this part was already sort of well known from other models. I decided to focus mostly on metasomatism because no one actually ever studied just the single fluid interacting with the rock. But overall, if I could choose let's say, the order of importance, I would definitely say that magmatism is more important because it's the primary, let's say, geological process. And then there is metasomatism, definitely sort of a smaller scale, but the good thing is that fluids can actually travel a lot. And that's therefore maybe also a much broader metasomatic environment than what we will think actually. So yeah.
Okay, I have another question. Can you explain a little bit the underlying mechanism for the different results you got? For example, you said that between Dunnett and Gabriel, it's more efficient for interaction between fluid and Dunnett to produce methane. So what's the underlying cause for that?
Yes, this is a very good question, actually. So as I show you, like in the deeper water model part, deeper water model works with species. Now, these species actually control the metasomatic interaction, which means that the fluid species are actually what controls the different new metasomatic minerals and the new, let's say, metasomatic fluid, the variation in geochemistry of such fluids. Now, if we look actually at this table here, the dunite is actually the richest, basically the magnesium richest rock we've got in the among these five. You can say yes, also orthoperoxenite, yes, but orthoperoxenite is mostly based by orthoperoxene, which stoichiometrically contains less magnesium than olivine. So dunite is absolutely the magnesium richest rock among the one I studied. And this is very important because there is a specific compound, it's magnesium, basically HCO3. If you add magnesium, you can have, I actually forgot the name, but it's one of the major species compound with formate, but you don't actually see them at the end because they are very important during the whole metasomatic process, but they keep reacting, and they keep reacting forming methane. So generally speaking, you have higher amount of magnesium, therefore you have higher magnesium richer species, and therefore at the end of the whole metasomatic process, you have more magnesium. So this is why basically dunite is almost the best. Clinoperoxenite is slightly different because the same works with calcium, and so as far as magnesium is dominant, it's just easier. But when you have both calcium, magnesium, and actually iron, there is sort of competition between them. But as you can see here, at the end, gabbro is the worst one. And if you look at the gabbro composition, there is a lot of plagioclase, a lot of calcium. Therefore, the calcium species are actually the worst. So in order, higher the amount of magnesium, or higher the amount of magnesium-calcium ratio, let's say, the better is the lithology. The lower is basically the worst. So it's all related to the carbon speciation during the metasomatic process.
Okay, thank you.
All right, thanks.
Next question, please. Okay, I have a question. Before the next question from participant. So could you move to the previous slide of the redox invert from the meteorite? I think that's one that, yeah. Meteorite is a source of information. Actually, I have two relevant questions right here. So first, it is counterintuitive to me that, for example, the Martian mantle is more IVO rich compared with the Earth's mantle. And therefore, I would expect that after the core mantle segregation, the core mantle oxygen fugacity at Mars is more oxidized than the core mantle redox of the Earth. That's the first thing. And the second is that in the Earth system, it's well known that in a closed system with increase of depth, we would expect to see the decrease of the oxygen fugacity of the bulk rock due to the garnet composition. But in this case, it looks like the Martian ones is exactly opposite. So for this, these two questions are about the Martian mantle redox that looks quite counterintuitive to me. So could you clarify?
Yes. So well, it's very counterintuitive, and the truth is, no one. I mean, we don't really know why. There are two main options. One, I truly believe that we are doing oxygen geothermobarometry on meteorites, and well, meteorites they are not just a hand sample. We got to Mars and brought them back to Earth, so they've been around for a lot of time, and such oxygen geothermobarometry might be sort of altered by all the thermal process from the meteorites coming into the atmosphere and so on. But at the same time, you're right. I mean, we see like a sort of inverted trend. So technically, we have an enrichment in oxygen in deeper pressures, and a sort of at shallower pressure, we have actually, sorry, shallower depth, we have actually lower oxygen fugacity. It's not entirely clear what is happening. One of the reasons that these are two different sources, which might just be very specifically constrained just a very narrow geological environment, or it could be that during the mantle segregation, and better, sorry, during the, let's say, Mars evolution, when, yes, mantle segregation, different layering of the planet, well, it didn't happen quite good as happened on Earth. Earth is much more, let's say, fixed and somehow, so the layers are much better defined. On Mars, actually, it lost basically its geological activity very, very soon. So one of the reasons that I read actually in literature is potentially the crust is sort of more, went through many more interactions, magmatic interaction, and somehow it's so carbon rich that actually we have a very reduced environment. If we go narrow deeper in the mantle, apparently there are still some oxygen reservoirs that are not well understood. So this is everything I can tell about the distribution of oxygen fugacity into the mantle. But yeah, that's it.
Yeah, I mean, even you follow this trend, let's say you extrapolate, go really deep, all the way to Martian core amount boundary pressure, for example, 25 GPa.
Yeah.
Uh, we would expect to see that it ends up at somewhere at the redox of delta M of Q, for example, minus 3 or minus 4. I think that's the
Yeah.
more expectation for them.
Yes, I believe that will curve back to FMQ at some point. It's very likely that it's completely different than Earth. I mean, I know there could be some oxygen, let's say, reservoir in Mars, and as you can see from also this here, we have two different water contents between Martian crust and mantle, but it's very unlikely that deep into the lower mantle of Mars we have very high oxygen fugacity. After all, it's been during the Martian evolution must be sort of released and brought up to the surface. So I suppose we'll be closer to what we have on Earth.
Any more questions from our participants? Okay, I think with that, we can wrap it up today. And thank you very much, Dr. Rinaldi, and thanks everyone for your participation. So I hope that this video posted on YouTube will be watched by more people that are interested in web about our webinar and as well this talk, but could not participate in time. So yeah, okay, thank you very much.
Thank
Thanks
you
a lot,
very much for
everyone.
inviting me.
Yeah, I will send the YouTube link to you
Thank
of
you
your
very
talk.
much.
You could share with other people that are interested in your research.
Thanks.
Okay, great. Thank you very much. Bye bye.
Thank you very much. Goodbye.